So, couple of things we need to remember, whether it's from your Algebra 3-4 class, pre-calc, or maybe you just learned it for the first time in here, okay? But, just as we are looking at this, guys, the limit as x approaches infinity, okay? What I am looking at is something with the highest degree, okay? Like, we're going to be dealing with some polynomials where their degrees are like 3 and 4 and whatever. When I say this, and when I say x to the n, I'm looking at the one with the greatest degree, okay? So what are the coefficients in these two problems? The coefficients are the numbers in front of the x. So it's a 1 over 1. And do you guys see how these powers match? Okay? So because I have 1 over 1, that means the limit as x goes to infinity is just going to be 1. Okay? We're not there yet, mean girl. Okay? It'll clear up. It'll clear up. Maybe. Maybe not. Come on. What is it doing? I will not talk dirty to you, okay, machine? Like, oh my gosh. Okay, the limit as x approaches infinity of something with x to the n over x to the n. Now understand, if I'm adding a constant, this constant is not in the fraction. It's off to the side, okay? So this would just end up being 1 plus that constant, the c value, okay? So again, the limit, and these are just, I'm just reviewing these, the limit, no. Oh, kitty, warm kitty, little ball of fur. Kitty, sweet kitty, purr, purr, purr. Guys, I don't know what's going on with this today. Okay, so now understand, I am now changing the coefficients in front. Like, let's just call this random coefficient letter A, and let's call this random coefficient B. Okay, so it's just x to the n still. So in this case, your limit as x approaches infinity is going to be A over B. Okay. Now, what happens if these powers are not the same? So the limit as x approaches infinity, let's say this is just x to n plus 1 all over x to the n. Okay? And what you guys need to remember is that this means x to the n times x, right? All over x to the n. Do we see anything canceling from top to bottom? X to the n. Yeah. So that means as x goes to infinity, what is this going to do? It's going to shoot off to x. In other words, if I plug in infinity, it's going to go to infinity. Okay. And then lastly, if I have a greater denominator, the limit as x approaches infinity, I have x to the n in the numerator all over x to the n plus 1. It doesn't really matter. It could be like plus 10, plus whatever. So, okay. So all I'm trying to make you guys understand is we're just looking at which side has the greater degree. Okay. So in this case, the denominator has the greater degree. So, again, it's still going to cancel. You're going to end up with 1 over x. But this is a little bit different. What happens if I plug in larger and larger numbers in my denominator? It's going to get smaller and smaller, and it's going to try and get to, not negative, 0. Okay, it's going to try and get to 0. Okay? So again, this is just a really quick recap of what you should have seen. Now, let's do some examples of why this might be important. Okay? So, example 1. Let's say the limit as x approaches infinity of the function 5 minus 1 over x squared. Okay. Well, some of us might be able to understand what this is, but we're actually going to prove what it is. Okay, so see how we have 5 and it's being subtracted? What we're allowed to do is we're allowed to break up this function into 2 parts. We can say it's the limit as x approaches infinity as it goes to 5 minus the limit as x approaches infinity as it goes to 1 over x squared. And then if we took these limits individually, well, guys, what's this part going to be? It's just going to be 5. You can't change it. It's always going to be 5, right? So here I get 5 minus, now as we look at this, where's the greater degree? Is it in the numerator or the denominator? In the denominator. And if we go back up to those rules, if it's greater in the denominator, it's going to equal 0. So that means the limit of this function as it approaches infinity is just 5. Okay? So.
Do we write limit as x approaches infinity equals 5 though?
Yeah, we can. But we have to write out the entire function because it wasn't defined. Okay? There's a 1 there. So, you guys cool on that part? Yeah? Okay. Okay. So here's example 2. Now, the limit as x approaches infinity, we're going to have a rational function, so 2x minus 1 all over x plus 1. Now, I'm not sure how you guys would have learned this, but when I taught it back in 3-4, what I said we're only worried about the thing that has the highest degree. Okay? So looking up in our numerator, which of these has the highest degree? Is it 2x or is it minus 1? The 2x, okay? Because this technically has like x to the 0, if you can imagine it. Does that make sense? Because x to the 0 would just be 1. So this is my greatest degree up in the numerator. Okay? So I'm only going to focus on that. What's my greatest degree in the denominator? It's x, right? So looking at this, are my powers the same, yes or no? Yes, they are. Are my coefficients the same? No. So then I revert back to this rule of, oh, it's whatever it is over b, right? So in this case, I'm going to get 2 over 1, which is just going to be equal to 2. We okay? Like, this isn't calculus. This is just review, kind of. We're getting to the calculus. All right. 2 more examples, and we're going to talk about L'Hopital's rule. Okay? So the limit as x approaches infinity of x all over radical x squared minus 4. And it just got complicated.
Not really.
You don't think so?
Because you just turn it into an exponent.
Explain.
Because the radical is basically what's underneath it to 1/2.
Mm-hmm.
You can work with that, explain it.
Okay, so hang on. So, what can you guys agree that the numerator is going to be? What's the highest degree there? It's just x to the power of 1. Okay, so we can get on board with that. It's x to the power of 1. The question is, what's more important, the x squared or the negative 4 here?
X squared.
The x squared, especially if I'm approaching infinity, right? Like, that's going to drastically change it more than the negative 4. But what do you have to remember? You're taking a square root. So this is what I'm really dealing with. I'm really dealing with the square root of x squared, right? Does that simplify any more, or do I have to interpret what that means? It simplifies, right? What does it simplify to? Yeah, so when I have x over x, are my coefficients the same?
Yes.
Yes? So what is my limit then?
1.
Yeah. So this limit, as it approaches infinity, is 1. Okay. So let's throw a little bit of a curveball. We've only talked about if it approaches positive infinity. Let's have it approach negative infinity. So the limit, as x approaches negative infinity, of the function x cubed plus 2 all over x squared minus 1. Okay. Greatest degree in the numerator is x cubed. Greatest degree in the denominator is x squared. How could I break this apart so I can understand it? I could do x times x times x. Or, think about the rule that I applied. I could subtract. We are going to cancel out, but here's what I want you guys to see. This is also x squared times x, correct? Okay? All over x squared. Do you see where I'm going with this? What I'm trying to do is, like, these will cancel, okay? So, like, as I do this, the limit as x approaches infinity of x is just going to be what? Negative infinity. Okay? So that's a nice little review. Let's get to the calculus. Okay? Why this might be important. So, are we good? Cool? All right. So, what we are going to talk about is L'Hopital's rule. And here's how you spell it, and he must have been German or something, or I don't even know. He's French. There you go. Okay. L'Hopital. L'Hopital. He's French. Yeah, this L, whatever that is, apostrophe H. No, L'Hopital. I know, it looks like hospital. Maybe he was born. Well, there you go. I don't know, maybe he discovered it in a hospital. I don't know. Maybe it's just his name. Okay, I mean, I'm not really one to judge on last names. Mine is Seaman. So, okay. Now. Okay. So, guys, here is when we are going to use this rule. You don't know what it is, but it's important to understand when we use it, okay? So, we do this when the limit produces, I know, a 0 over 0, which means it could have a whole, right? Infinity over infinity, or negative infinity over infinity.
Wait, so why would it infinity over infinity just be 0 or 1?
Because which infinity is growing quicker? Okay? So that's what you don't understand. Like, that's why we have to use L'Hopital's rule, because we're not understanding, like, we understand the concept of infinity, yeah, it goes on forever, but it's hard to imagine which one's growing faster. Okay? All right. So, ladies and gentlemen. Oh, thanks. Okay. So, if the limit as x approaches c, now realize I'm dealing with two different functions, f of x over g of x, and usually they're rational functions, okay? If it produces this 0 over 0, or infinity over infinity, or negative infinity over infinity, then, dot, 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 we are allowed to do this. The limit as x approaches c of f prime of x over g prime of x equals L. This is the limit. And the reason we could not do it before is because in Chapter 1 you guys didn't know derivatives. But now that we've gone through Chapter 2, you know how to derive things. So we can use this process. Okay? So, let's get into some examples where this is actually true. Okay? And one of these... No, I'm just saying, what's the way I want to explain it? It is always true, but some of these, like, I've seen a problem where you would have to take the derivatives 99 times to understand it. There's also another thing that you guys aren't learning this year to make it go faster, but you're not learning it right now. Okay? Okay? Yeah. So let's just get into example 5. Okay? So, I made you guys do this the long way. The limit as x approaches 0 of sine x over x. Now let's remember, I'm not plugging in infinity this time, right? What are you approaching? What's the limit approaching? 0. So we're like, the first thing I've always told you guys is just plug it in and see if it gives you anything. So what's sine of 0?
0.
It's 0. What's 0 when I plug it in?
0.
0. Okay, perfect example. So, I have a 0 over 0. We see this. Therefore, now we can use L'Hopital's rule. L'Hopital's rule says take the derivative of the numerator, take the derivative of the denominator, and then again, plug it in. So, what's the derivative of sine x? Cosine x. What's the derivative of x? 1. Which is kind of nice. It kind of looks like it's going to take care of my problem. So again, what is the limit as x approaches 0, where I'm going to plug it in? What is the cosine of 0? It's 1. And there's nothing to plug into in the bottom, so it's 1. So now I get the limit is 1. So now you've just found a limit where before we weren't able to do it, because it was 0 over 0. So don't forget, it's actually the limit as x approaches 0 of sine x over x is 1. We use this is where we use the, how do they do it? Is it LH hat or something? What's the okay, L hop. So, okay, I'm just showing you guys that's where we used it. Yes.
So it's only if it's 0 over 0, not if it's like 2 over 0 or something?
Correct.
So it's only if it's those three things, then we can use it.
Exactly.
Can you give it a 0?
Yes, I can. So, example 6. So the limit as x approaches 0, and let's make it a fun one, 2 sine x minus sine 2x all over x minus sine x. Okay?
It's a lot of fun.
I know! So you better know your trig, right? But guys, what are we approaching? So the first thing you guys have to do is you have to plug it in. You can't just assume this rule is going to work, because sometimes it might actually equal a limit. So here, what is sine of 0? 0. So this is 0 minus 0. In the numerator, you do get 0. This is going to be 0 minus 0, which is still 0. We have just proved, now we can use L'Hopital's rule. So L'Hopital's rule says, take a derivative. Okay, derivative of 2 sine x. 2 cosine x. Derivative of negative sine 2x. Negative, it's a chain rule. So yep, minus 2 cosine 2x. Derivative of x is just, I can dig that one. Okay, derivative of sine is cosine, so minus cosine x. Now guys, remember, I don't have to make anything crazy. All you have to do is go in, plug in. Okay? So let's see. What's the cosine of 0? 1. So this is actually like 2, right? Because it's 2 times 1. Cosine of 0 again is 1. So minus 2. And then on the bottom I have 1 minus, what's cosine of 0? 1. So I have 2 minus 2, which is 0, over 1 minus 1, which is
0.
Guess what?
Second derivative.
Do it again! Yeah.
So cosine 2x, we would have to do 1 divided by 2. Or 2 times 1, and then it's
Guys, no. What's 2 times 0?
0. Oh.
That is on the inside of the cosine function. It's your x value times 2. So 2 times 0, then take the cosine. Okay? Alright, so we're going to do this again. We're going to use L'Hopital's rule again. So let's see, hopefully it helps us, maybe it won't. So, what is the derivative of cosine? Negative sine, so negative 2 sine x. Okay, here we go. Derivative of cosine 2x is going to be...
Oh, it's a 4 negative sign.
Okay, so... It will be.
Oh, yes,
Yeah. So, derivative of this will be 2 times 2 is still... It's 4. The derivative of cosine is going to be a negative, so that's going to turn that into a positive. So I have positive 4 sine 2x. Okay. All over, derivative of 1. 0. So yes, that drops off. Derivative of negative cosine x will be sine x. And the limit as x approaches 0. So, what's the sine of 0? 0. Plus, what's this? You guys asked. 0. And then what's this? 0. So again, I get 0 over 0. We're going to do it again! I promise this is the last time though. This is it. Yep. Okay. So, let's do it one more time. And just to make this process go a little bit faster, I'm going to get minus 2 cosine, cosine x. This is going to be plus 8 cosine 2x. Derivative of the sine x is going to be cosine x. Now, the limit as x goes to 0 of this. Okay. Right here, I'm going to get negative 2 plus, this is going to be 8. So far we don't even have a 0 up top. That's good news.
Yes.
Cosine of 0 is 1. So I'm going to get 6 over 1, which is going to be, so let's bring it back. What does this mean? Okay. So that means this limit of that original function, okay, equals 6. That's what that means. But guys, it could have been worse. I could have made you like factor things out, made you multiply by some conjugates. I could have done that, okay? So, you guys good? We're not there yet. That's chapter 5. Alright, so example 7, and this is the last one. Example 7. The limit as x approaches infinity. Okay? So, you guys might already know the answer, but I just want to prove to you that L'Hopital's rule always works. Okay? So it says 4x squared minus 5x all over 1 minus 3x squared. Okay? I'm sure some of you guys are looking at this and you're like, okay, I can just apply that rule from the beginning. But what if we forgot all of our rules? Right? So let's apply L'Hopital's rule. What does L'Hopital's rule say? Yeah. So this is technically going to equal infinity over negative infinity. Okay? So imagine what would happen if I plugged infinity and squared it. It's going to infinity, and it's positive, right? If I plugged in infinity and squared it, and then multiplied it by a negative, it'd be negative infinity. Okay? So I have infinity over infinity. But the question is, which of these is growing faster, and is it going to converge or diverge? So what I'm going to do is we're just going to go and take derivatives. So, the limit as x approaches infinity, well, what's the derivative here of your numerator? 8x minus 5. What's the derivative of your denominator? Negative 6x. Again, you guys are probably looking at this, you're like, do I really, like, I can kind of see what's going to happen, but what happens if I plug in infinity? You're going to get 8 times infinity, which is just going to be infinity. You're going to get negative 6 times infinity, which is going to be... So again, it gives me infinity over an infinity. So one more time, apply this rule. So I'm going to get 8 over negative 6, right? So this is our answer, but does it simplify?
Yeah.
To what? And this is proving why that rule on the first page worked. Okay? Because look at the coefficients of x squared here. It was 4. Look at the coefficient of x squared here. It's negative 3. Our limit is 4 over negative 3. Okay? You guys see it?
I see it.
Okay. So, infinity?